Welcome everyone, my name is Ting Luo and I'm postdoc in Max Planck Institute in Düsseldorf. Today I will focus on half-Heusler compound of niobium-cobalt-tin system. We characterize the grain boundary segregation and the nano-precipitates by atom probe tomography. We will see how these features influences thermoelectric performance. Thermoelectric materials could directly convert heat gradients into electricity, and the performance is characterized by figure of merit Zt, which is related to Seebeck coefficient, electrical conductivity, and thermal conductivity. Half-Heusler compound have a composition of XYZ. It consists of 3 interlaced FCC sublattices. In the half-Heusler family, there are many compounds. Niobium-cobalt-tin is a promising candidate for thermoelectric applications. The 3 constituents are abundant elements, and the niobium-cobalt-tin also has favorable band structure to achieve better Zt. We used platinum as the dopant in niobium-cobalt-tin, and we prepared a series of samples with a large composition range of platinum, with X from 0 to 0.15. The thermoelectric performance of this series of samples is published in this paper. Here we will just focus on the one composition, which have X equal to 0.06. The electrical conductivity of this sample increases with temperatures at the beginning, and it indicates grain boundary scattering of carriers, and which means that the microstructure of this sample would play a very important role. Here we found that the grain size of this sample is quite small after ball milling and spark plasma sintering. The average grain size is around 230 nanometer. Then we prepared APT tips on this sample. We found grain boundary segregation and nano-precipitates in this sample. In this APT volume, we observed the 4 grains, and we plot the 1D composition profile crossing different grain boundaries, and we found that these profiles are quite interesting. First, the peak composition of platinum and tin are not aligned in the same position, and we found that the peak composition of platinum always corresponds to the depletion zone of tin, and the depletion zone of tin is only present at one side. This is an indication of grain boundary aggregation. If you assume that in the initial state, grain boundary is enriched with B elements but depleted in A element, and after grain boundary aggregation, A will pile up ahead of the grain boundary, while B will segregate at grain boundaries. And this is what we exactly observed in the 1D concentration profile of this sample. We also found nano-precipitates in this sample. After a detailed analysis of APT dataset, we found that nano-precipitates are enriched with niobium, but they have different compositions. The first large precipitate is also enriched with carbon, nitrogen, and oxygen. The content of platinum in this precipitate is around 15 atomic %, which is much larger than that in the matrix. And the higher content of platinum is also observed in carbon nitride and carbide, while in the niobium oxide, the content of platinum is lower than that in the matrix. And this observation is consistent with what we observed in TM. In TM, there were 2 different kinds of nano-precipitates. These brighter precipitates should be enriched with platinum, and these darker precipitates should be niobium oxide, and they are depleted in platinum. Carbon, nitrogen, oxygen should be introduced during the process of ball milling, and these nano-precipitates could help to increase the scattering of phonons, therefore decrease the thermal conductivity. Conclusion: in niobium-cobalt-tin system, we found that platinum dopant distributes not only in the grain interior, but also segregate at grain boundaries. And this grain boundary segregation should be taken into account when we try to interpret the grain boundary scattering of charge carriers. Two types of nanoprecipitates are found regarding the interaction with platinum dopants. And if these nanoprecipitates could be introduced in a more controlled way, the thermal conductivity of this sample could be decreased by nanoprecipitates. And thank you for your attention.